Hello everyone, this is Mr. Ponce, and we're going to go ahead and get back into kinematics again. Today, we are actually focusing on the final part of kinematics, which is acceleration. Now, already we've discussed displacement, we've discussed velocity, and you've seen already how the two are related in what we have, or what we call the x versus t graph. So we've actually experimented with this, and we've seen, how you go ahead and find the velocity based on an x versus t graph, which is when you go ahead and you find the slope or the rise over run. And then after we went ahead and also found what is the equation that dictates this. Now, obviously, that equation was barring any acceleration as part of it. And we've also experimented, how acceleration can affect motion. So the other thing we've been doing lately is actually just kind of going ahead and taking our x versus t graph and involving some acceleration. And we saw that, this creates like a parabola of some sort, just your basic parabolic motion. So this is what happens when you get acceleration involved. Your velocity changes, and this straight line that was once linear now becomes more parabolic. So now you have an acceleration involved, and no longer you have a straight line. So what we're going to do today is actually we're going to go ahead and add some of these procedures that we had on an x versus t graph to a v versus t graph, which is this next level up. And you notice this graph, even though we have acceleration, is linear. So that does make it easier for us to go ahead and calculate these things. We cannot exactly find acceleration without some very hard work on a parabola, but we can find it on a v versus t graph, and hence the reason we're here. So we're going to go ahead and add some of this stuff that we did with an x versus t graph onto this v versus t graph this time, and we're going to see what we can find out. So we're going to start off by finding the acceleration. So we're going to find A. Okay, so let's go ahead and get started with that. Now, if you remember, on an x versus t graph, in order to find in order to find our velocity, right? We went ahead and we actually took the slope of the graph, right? And when we took the slope of the graph, we found the rise. Here, I'm going to change colors here. We went and found the rise. In other words, we found our delta x, right? And then after we went over and found our run, which was delta t. And notice that is actually the velocity equation, right? So we got our rise over run, or our slope, and that was our delta x over delta t. Now, if we go ahead and try it on this graph, you'll notice you'll get the same thing, right? Let's go ahead and let me write it out for you right now. So let's say you want to go ahead and do it to this graph, right? If we took our rise, right? In this case, let's go ahead and say we're going to here, right? Notice it'll be going from 0 to 40 meters per second, because that's the unit. And that makes it delta V, right? So the slope here is delta V. Sorry, just realized I wrote delta X there. Force I have it. This is delta V, right? This is our change in velocity. And then after we go ahead and take a look at this, right? And then after let's say we want to go this way. Notice this here is still time, right? This here is still time down here. In other words, so this is still a delta t down here. And usually you'll find out that'll be the case whenever you have a graph, right? Usually when we graph things, we like putting t on our x-axis because usually everything is dependent on time. And you notice when you do this, this goes back to the acceleration equation that we learned. So finding A is dependent on delta V and delta T. So what we're going to do is that we're going to go ahead and find the slope of this graph. So I'm actually going to do the entire thing. I'm going to do this subset region here that I've highlighted in beige. So let's look. Let's find our A here. Right? So let's look. Well, if you remember, if we are going to find this, we need to go V final minus V initial, right? And same thing, or delta V or delta T, but this is what delta V means. So delta T means time final minus time initial or starting time. And I decided to start a little off zero so I can go ahead and give you a little bit of a harder example. Let's go ahead and do this. So here we end off at 60 meters per second, but we start off at zero. So we start from here. Okay, let's go ahead and find our delta T now. Our final time is 50. And our initial time is 20 seconds. Okay, so you can see here, we can go ahead and let's do the math here. 60 divided by, 60 meters per second, right? That's the end of this. Divided by 30 seconds. Now what's going to happen here is when you get the divided by 30 seconds here, you're going to actually tack on an extra seconds here to this unit. So 30 divided by, 60 divided by 30 is 2. And you notice once you have the seconds here, you're going to tack this on. And you're going to meters per second squared. Okay, that's just kind of the nature of it. And that is an acceleration here. Notice when you have seconds squared, it means essentially you're taking the change of velocity over time. You're measuring how the velocity is changing as time moves on. So hence the reason you have another squared or another unit of time added to the bottom. And this is going to be our acceleration. Now, you notice actually this actually matches this value here. So it tells me that I have the right answer.